These buildings are among the biggest man-made objects. They have been moved many kilometers across the sea and sunk down to incredible depths. They are made of reinforced concrete, built in massive mobile and floodable construction sites, then tugged to their final resting place. Troll A is the world's tallest building, and the Gullfaks Sea is the heaviest object ever moved. They were the first in a long line of massive oil platforms built over the last 2 decades that use gravity and suction to remain upright in the stormiest of seas. But it was the Hebron project, whose 65,000-ton topside was the biggest ever moved when it was towed from Korea to Canada, that broke heavy lift records when the whole whopping 750,000-ton megalith was finally maneuvered into position. Oslo, Norway. This is the head office of Kvaerner, famed the world over for its concrete mega-structures. Everything it builds is big. Indeed, it has built not only big oil platforms, but the biggest. Far out in the North Sea are 2 oil and gas fields, the Troll A and the Gullfaks Sea. Resting above them are 2 of the world's largest structures, respectively the tallest and the heaviest. Off the coast of Newfoundland, 2 other platforms, the massive Hibernia and Hebron, moved into place in spectacular fashion. The Hebron has the biggest topside in the world. When construction on the massive structure was finished in Asia, it was towed in a mega move halfway around the world to be installed onto the platform base in Canada. Kvaerner is specialized in gravity-based supports, massive concrete bases that use gravity to keep an oil platform perfectly in place. Some of these concrete giants float and are held in place by cables, but others simply lie on the sea floor. Not so simply, as we shall see.
Hebron has the heaviest topside ever installed, so it's 65,000 tons weight when it's operating.
Hebron, the last one that was delivered last year, is 133,000 cubic meters of concrete. Troll is 220,000 cubic meters of concrete, and Gullfaks Sea is 240,000 tons of cubic meter concrete. When it comes to concrete, because concrete is a bulk material, that is always numbered in cubic meters. Not tons when it comes to comparing sizes and so on.
The wild North Sea and northwestern Atlantic Ocean are among the harshest environments in the world. And yet, it is here where some of the most strategic oil and gas fields lie. Icebergs, earthquakes, and winds up to 100 kilometers an hour are just a few of the dangers that await the brave few who venture here. Indeed, the first freak 25-meter wave was recorded in the North Sea on an oil platform. This is the bustling modern city of Oslo, Norway. One of the great centers of the Viking explorers who braved the North Atlantic in open boats to discover the Americas, a historical connection that still ties Canada and Norway. Oslo was also the home to Roald Amundsen, whose ship Maud has recently been saved from the great Canadian North by adventurous salvors. The two countries share a unique understanding of the Arctic North and have learned how to build enormous structures that can survive in the hostile environment. For 3 decades, Norwegian, British, American, and Canadian companies have drilled the seafloor here to extract the black gold. At the heart of the operations was Kvaerner, one of Norway's most experienced oil platform design companies. Kvaerner's story starts in the mountains near Oslo more than 150 years ago, when water mills provided essential energy for manufacturing. With the Industrial Revolution, Kvaerner and their competitor at the time, Aker, began building ships, turbines, stoves, and tools to supply Norway's industrial development. When the North Sea oil fields were discovered at the end of the 1970s, both companies started building oil platforms. They specialized in a type of oil platform called a condi, a concrete platform that sits on the bottom of the sea, using gravity alone to stay upright. In 2002, the two companies merged, and in 2011, Kvaerner was split off as a pure engineering company focused on designing and constructing oil platforms. Here in Fornebu, near Oslo, at the Kvaerner headquarters, Catherine Rusten Haldorsen and Guro Løken work to see that the oil platform projects are not only built safely, but floated to their site of operations successfully.
I'm responsible for marine operation and decommissioning in Kvaerner. So when I joined the company back in 1996, we had just finished towing out the Troll A platform, which is often referred to as the 8 wonders of the world. So I thought that was just amazing for me as a young engineer coming, seeing this operation. And for Troll A, as you might know, it's 472 meters tall. So if you compare that with the Empire State Building, that's huge. The Empire State Building is 442 meters. So for me, Kvaerner was a company that built and installed the most fantastic platforms.
I must say that the worst thing that ever happens is if people get hurt. We want our people to go home safe from work every day.
The engineers and designers at Kvaerner must be confident that no matter how big of a structure they build, they know it will float and survive even the most challenging weather conditions.
The reason why a concrete platform floats is actually that the uplift and the weight is equal, and then we get it to a floating position. You might know about Archimedes' law, and that's the basis for all of this. Basically, when Archimedes put himself into a bathtub, he saw that the displaced water was the same amount of as his weight, basically.
The traditional laws of physics remain the guiding principle, but it is the tried and true engineering experience that assures the platforms are built to last, whether in the ice-clogged North Sea, the northwestern Atlantic, or the placid Adriatic. The North Sea oil fields were first discovered in the 1970s, just as the world was undergoing its first great oil crisis. However, getting to drill there proved a Herculean task. the Norwegians had a solution. The Condeep is an incredibly deep concrete structure that lies on the sea floor and holds the oil that is pumped in massive reservoirs. Catherine Ruston Haldorsen is the head of concrete constructions at Kvaerner and has seen many Condeep sail out of Norway's deep fjords.
Condeep is a concrete deep water structure. And the concrete platform may include oil or gas storage inside, 1 to 4 shafts, mechanical outfitting, and of course drilling equipment. And of course one important feature is it is the foundation for the topside. But I think maybe that in the very early stages, you know, with the extreme water depths, they did not have the technology for anchoring structures to the seabed. Today you see a bit some other solutions than what we had in the early beginning of Condeep platforms.
One of the most challenging oil and gas reservoirs is the Gullfaks field, 175 kilometers northwest of the Norwegian coastal city of Bergen. In the 1970s, 3 Condeeps were built to extract oil, but the last Gullfaks C proved to be a record breaker. The sea floor of the Gullfaks oil field is made of meters and meters of soft clay with the consistency of yogurt. The place was a slope down to the Norwegian trench. Getting at it was incredibly difficult.
Well, of course, if you have a very solid ground, stable ground, you don't necessarily need skirts. But of course, if you have a soft, more yogurt type of soil, you need to ensure that the platform is anchored well into the seabed. And you may use grout and of course air evacuation system to get the trapped air out from the structure.
Protecting the sea from pollution and humans from accidents has become an overall priority for all companies all over the world as oil tankers, wells, and platforms have grown bigger.
It's now clear the explosion that ripped a North Sea platform apart was the world's worst oil field disaster. A task force of naval and civilian ships is still searching 700 square miles of sea around the Piper Alpha platform tonight.
Exxon Valdez, gouged by a reef, more than 8.5 million gallons poured into Prince William Sound, a prime fishing and recreation area.
Frantic efforts underway right now to try to prevent an environmental nightmare along the U.S. Gulf Coast.
Construction techniques in the North Sea and open Atlantic today build on experience from the past to keep workers and the environment safe from such hazards. Platform moves are meticulously planned in simulation centers, for example, and there have been advancements in the core materials such as concrete so it holds up in harsh ocean conditions.
The salt water around the concrete is absolutely no problem. Basically the concrete does not absorb any water. It's very dense and very waterproof.
In order to ensure that the Gullfaks C platform stayed stable and upright, Norwegian contractors' engineers came up with the idea of building concrete skirts that would sink into the clay for 34 meters to provide the horizontal stability and anchoring. They would be sucked into the mud and held in place by concrete grouting that would fill any spaces left for the vacuum to leak. It was an ambitious project and required more steel than it would take to build 15 Eiffel Towers and 200,000 tons of concrete. Construction began in 1986 in a 14-meter-deep dry dock. Many months later, the 16 concrete skirts had reached the required height of 34 meters. Then came the construction of the bottom of the oil reservoirs, again, more steel and more concrete. When no more could be done on the land site, and the construction yard was flooded, the base of the Gullfaks Sea oil platform was floated out into the fjord. The Norwegian fjords offer platform constructors a unique advantage because they are deep. Even deeper than the surrounding mountains are high. The base of the platform was surrounded by barges and boats, and now the upper part of the oil reservoirs could be completed, and then the 4 massive shafts constructed on top of them, slightly leaning inwards to better access the wells and for center of gravity. Now that the construction was complete, the first of the huge lifts that would turn this mass of concrete into a platform could begin. In order to do this, the 330-meter-tall structure had to be towed through the fjords of Norway from Vats to Stord, where the topside was awaiting it.
When we are designing these platforms, of course, you need to make sure that you have something called the center of buoyancy for the platforms, and you have something called the center of gravity for the platforms. So when we are designing platforms, we have to ensure that we have sufficient stability for towing these platforms out. If the stability is not big enough, then you start rolling and you might actually tip over. I mean, basically, when we do tow out of platforms, we have to ensure that we have a positive GM, is what we call it, geometric metracentric height for the platforms.
This is the most delicate moment of the whole construction of the Gullfaks platform. The concrete towers need to be sunk so that just 7 meters are protruding from the sea surface. This means that the narrower sections of the 4 shafts are under more pressure of water than they were designed for. So, any sign of cracks or leaks would stop the whole operation. It is thoroughly checked as the barges carrying the topside move slowly towards the shafts. The fleet of barges and tugs approaches the concrete structure, and compressed air is pushed into the barges to lift them to the required height. When they are over the structure, they can be reballasted, and slowly the topside sinks onto the towers, the mating complete. Now the whole platform could be raised to its full height out of the water, and pressure on its sides eliminated. A dozen tugs with 160,000 horsepower were needed to move the behemoth, featuring a displacement of 1.5 million tons.
Gullfaks is the heaviest object ever moved. It's 1.5 million tons. So if you have 1.35 million mini beetles, that is what you're actually towing out. And you can imagine doing that with 12 vessels, maneuvering these through the narrow channels is a fantastic sight. You also have to remember that when you have 1.5 million tons moving, it's not that easy to stop it. So that's why we have to do it slow and in a controlled manner.
The Gullfaks Sea platform was towed slowly through the fjord out to sea by tugs. On the 8th of May, 1989, it arrived on site despite heavy seas. Oil pipes had already been laid to other platforms in the field, so it had to be positioned perfectly. Water was used to ballast the skirts evenly. Slowly, suction devices pushed the skirts more than 20 meters into the clay. Any gaps were filled with concrete to keep the vacuum perfect. But the records set by Gullfaks Sea platform were to be shattered by a new con-deep built in Norway 10 years later.
A concrete platform that is placed on the seafloor, like Troll and Gullfaks, you can have enormous topsides. So, of course, if you have a floating platform, it's limited how much weight you can have on board. And because if you have a huge, the bigger the topside is, the bigger the hull has to be in order to keep floating, basically, to get enough buoyancy. So often, I mean, when, like in the North Sea, you see that you have around 300-400 meters. We often have con-deeps, as we have explained, but when you go 400-500 meters, we end up with the semi-submersible or TLPs, like we have on Heidrun, or FPSO, like you see on Varg and other fields.
If Gullfaks was big, then a decade later, the Troll A project was even bigger. At 470 meters tall, it was, at the time, the largest ever energy project supplying Europe with clean natural gas. The Troll gas field is located in the Norwegian Trench, so even deeper than the Gullfaks oil field. The platform that Aker designed and built in its Stavanger plant became the tallest building on the face of the earth. Here too, the platform was designed to be kept in place by concrete skirts that would dig deep into the soft sea floor, sucked in by vacuum. However, although the technique had been tried and tested before, Troll A's height posed some serious problems for designers. The Norwegian fjords, in their stark beauty, are the legendary home of Norway's favorite monster, the troll. The name of the deepest and most dangerous natural gas field, therefore, seemed appropriate, and the monster that Aker, Kvaerner's sister company, built fits the description. It was designed to resist the highest waves, the worst storms, and even earthquakes. The Aker dry dock in Stavanger is the site of construction of the skirts of the Troll A platform. Now came the time for the very first of the towage operations that made the construction of Troll A and its positioning on the sea floor such a spectacular event. The dry dock was flooded and the huge concrete structure began to float. It was towed out to the adjacent fjord to be continued. Out in the fjord, the oil reservoirs were covered with their dome caps and construction began on the shafts. However, once they had reached 60 meters in height, the platform had to be moved again. The fjord here simply was not deep enough.
Basically, part of the concrete platforms is always built in a dry dock. And depending on the total height of the structure, it could be completed in the dry dock, but very often we have done the first part. Then it's being towed out to a deep water site where the remaining structure has been completed. And in some cases, the topside deck is mated in the deep water sites. We try to do as much of construction in the dry dock as possible. Constructing in a deep water site does increase the cost because of all the flotilla, all the barges we need to maintain offices, services and so on in the floating stage.
Construction was fast, as the company employed a new technique known as slip forming, which minimizes the time it takes for concrete to dry, making for a smoother and stronger surface. Once the deeper fjord was reached, The box girders that served to harden the very tall structure were built. These were prefabricated steel structures that were then encased in concrete to stop the four shafts from swaying with the waves. In the meanwhile, workers got on with building the ancillary equipment, the pipes and tubes, electric circuits and gauges.
The majority of the construction method is based on slip-forming technology. It's an hydraulic system that lifts up the forms, and the reinforcement and the concrete is being executed 24 hours a day. So weekends, Christmas, all days. This has many advantages, and that is you reduce the amount of casting joints. So in principle you get a better quality, you get a watertight structure, and of course it's quicker to build. So you save overall construction time for the projects.
Troll A was designed so that the deck was long and narrow, keeping living quarters far from the derrick and working area as an added safety measure. This, in turn, means that the drill shafts are central, while two support shafts are external. As construction continued, the shafts were sunk deeper and deeper to allow better access to the segment under construction. Then came the third great heavy lift operation of the whole project. Time had come for the concrete support to be mated with the deck and all the equipment it carried. The concrete was sunk to within just 6 meters of the top, so subject to far more pressure than it was originally designed for.
For the platform, we have like permanent ballast system in the platform. But in addition, for these temporary phases, we have some temporary ballast pumps so that these operations can go fast enough, because we need to be, normally these operations are weather restricted, so we need to do it within a weather window. So we use ballast pumps, pump in water, pump out water in order to get out of the dock and also in order to mate the topsides on the platform.
Barges carried the long, narrow deck out to the shafts and were pumped with air so that it could be safely fitted over the 4 shafts. Every connection had to be fit perfectly for the mating operation, which was completed in 30 hours as the barges were emptied of air and the deck lowered. Once the connection had been made, the whole platform could be refloated to its full height. The refloating and towing is usually done when the North Sea weather is at its fairest.
We never know exactly what wind and waves we see, but on board these huge tows, we normally bring a meteorologist with us, and we have weather meetings several times during the day in order to make sure that it's no hurricanes or no unforeseen weather coming up, because then we have to either go into a safe harbor or hold the towing fleet for a while. When we do plan these operations, we do it during summer season in order to make sure that the weather is nice and we have predictable weather. But it's, I mean, what can I say? We need to do detailed engineering, and then we have it under control.
Higher than the Empire State Building, as tall as the Petronas Building in Singapore, the Troll A was the tallest man-made object ever to be moved. On the 10th of May 1995, the tow out to the Troll gas field began.
First of all, you have to maneuver your platform out from the dock where it's constructed. Then you fill water into the dock, and then you have to fill water into the platform so that it doesn't have uncontrolled liftoff. And when you go out of the dock gate, we often have harbor tugs attached to the platform. In addition, we have a towing tug getting us out from the dock gate. And we also hold back with something we called hold-back winches. And then we can ensure that we go smoothly out of the dock.
These massive platforms must be towed very slowly out of the dock and maneuvered in a very controlled manner out into the towing channel, never faster than 2 to 3 knots. Today, tests are done at a simulation center, first to make sure that all vessels are towing with the right amount of force to navigate the route successfully. But there must also be a clear chain of command.
So when we have decided what vessels we're going to use for the tow, we invite the captains, and also we always have a tow master. He's kind of the, if you're in the military, you have to have one guy that's in charge of the tow. So he's in charge of the tow and he's giving orders. So what we do is to rehearse the full operations, both the inshore tow and the offshore tow, with all the involved parties, so that we make sure that every small, like you asked, if we're going through a tight corner, we need to make sure that that vessel pulls in the right amount of force.
Tugs began moving the Troll A down the fjord. They had been over the route several times, virtually. The course took the convoy round a very steep bend, but also at some points the clearance between the seafloor and the bottom of the platform was a meter only. An uncharted rock could have stopped the convoy in its tracks and threatened to topple the platform. It took 7 days to go 200 kilometers. The heavy concrete bottom compensated for the tall structure, and when it was over the designated area where gas pipes have been laid, the skirts were slowly deballasted, keeping the whole structure vertical at all times to make sure that when it reached the bottom of the sea, it would sink evenly. In 1996, when it began operating, the platform set the Guinness World Record for the largest offshore gas platform.
Troll was designed for 70 years lifetime, which is extremely long. But of course the design principles and construction methods are similar. But of course continuous improvement and development of both design and method is very important to adapt to new standards and codes today.
A few years later, Aker and Kvaerner merged, and their engineering expertise was recognized the world over. In recent years, Kvaerner has worked on a number of mega projects that have shown that Norwegian know-how in maritime and hydrocarbon affairs is second to none. Kvaerner has built concrete and steel, oil and gas platforms everywhere in the world, but its speciality is concrete. Here on the Adriatic coast lies one of the most recent projects, specially designed to be low on the horizon and invisible from Venice.
One of the benefits with Adriatic LNG it is you have established a fake island away from the shoreline, so it basically does not disturb the people and the region there. The terminal itself was built in Algeciras, southern Spain, and towed to Italy. But the two concrete mooring dolphins, which is part of the LNG, was actually built in a ship dock in Venice and then towed out to the platform. The topside was installed in Algeciras in southern Spain and then completed offshore Venice.
The massive terminal is a liquid natural gas regasification plant, one of the largest in Europe, that supplies natural gas delivered by ships to the city of Venice and the industrial port of Mestre. While today's platforms may not break records like the Gullfax or Troll A, they are still marvels of engineering, and there is no shortage of demand for oil and gas extraction platforms across the globe.
During the new concrete platform age since 2003, Kværner has actually delivered 5 new platforms in Spain, Italy, Russia and Canada. And I think that is something that is not necessarily so well known anymore. I mean, we tend to focus a lot on these, let's say, previous wonders. But concrete is as applicable today as it was during the Troll and Gullfaks sea age.
One of the newest monster platform designs was actually built on the other side of the world in Canada. The Hebron and Ben Nevis oil field was discovered off the Grand Banks off Newfoundland in 1980, but taken more than 30 years to come online.
The concrete itself, there has been a huge development of concrete the last 20 years. Of course, concrete consists of cement, water, aggregate, sand and coarse. But there is also a lot of admixtures in the concrete. Or a lot is maybe not the right word, but there is admixtures in the concrete that could speeden up the hardening or slow down the hardening. It also makes it more fluid, so you can actually pour heavily reinforced structures. So I would say that with the development that there has been within concrete last 20 years, I see there is hardly any limit on where we can go when it comes to high performance concrete.
Just the base of the Hebron oil platform is 122 meters tall and 130 meters wide at its base. It contains 52 wells and weighs 40,000 tons, made up of 143,000 cubic meters of concrete and 8,000 tons of structural steel and piping.
Hebron, for example, was built to 27 meters in the dry dock before it was towed out to deepwater sites. But it depends on how wide the diameter of the platform is, and of course of the water depth in the dry dock. So we need a certain buoyancy to get off the dry dock basement and towed out of the dock.
The enormous base has the dual role of keeping the platform on the ocean floor and at the same time holding up to 1.2 million barrels of oil pumped from below the sea floor. Over the months, the huge structure began to take shape until it was ready to be floated.
Now, I say safety is an extremely important value for us in Kværner. And already in the early design phase, we start planning safe execution, and both for the construction phase, but also for the operational phase. Also, we are extremely proud of having executed Hebron, completed in 2017. We produced more than 23 million man-hours without any lost time incident.
As the huge platform base was floated out to sea for finishing, the second phase of the work could begin, the construction and later transport of the central topside, which included the drilling and utility modules. The dimensions rivaled those of the base, 183 meters long, 75 meters wide, and 113 meters tall, weighing 44,000 metric tons, but with the addition of the accommodation module and derrick, this will rise to 65,000 tons. The tools brought in to do the job were enormous. The des, or derrick, was delivered to the construction site by barge. Getting the derrick off the barge was in itself a delicate operation, as the massive steel building was a high center of gravity. the 3,900-ton drilling support system was delivered to the base. The steel units were delivered by barge and offloaded using SPMTs, or self-propelled modular transports. Transport engineers built 6 towers that were to hold the lifting and skidding system that were key to putting the drilling support system on top of the UPM. 16 strand jacks, each with a capacity of 750 metric tons, were mounted on the 6 lifting towers and attached to 2 35-meter girders on which, in turn, held the 12 skid shoes and 2 kilometers of skid tracks that were key to the movement. The structure was skidded onto the Dutch-owned ship Blue Marlin using 64 1,000-pud skid shoes. These creep along Teflon rails like caterpillars, extending their reach hydraulically and then closing, pulling the load along with it. Now the UPM arrived and had to be offloaded. Here again, skid shoes were the key piece of equipment, and over 2 days the massive steel monster was moved to the shore. It rested on a finger surrounded by sea, allowing barges and tugs to access it with ease, and eventually the whole structure could be lifted onto the massive base, which had been specially designed to withstand the ice and storms of Canada's frigid north.
In Canada, you have challenges with the icebergs. So of course, those platforms are designed for iceberg loads. While other places, you have different kind of ice challenges that you need to design for. Some areas we have earthquake that we need to consider. And of course, the other environmental loads like wind and waves are key factors for designing the structures.
Over 2 days, at a snail's pace, the module moved towards its final resting place. Once it was in place, the lifting towers had to lift the second module, the 3,250-ton derrick or des, into place. The Italian heavy lift company had been engaged also to install the living quarters of the Hebron oil platform. Over the course of the months, the construction of the living quarters was completed in the huge hangar where 2 gantry cranes lifted prefabricated units onto the basic living quarters structure. The living quarter module was 58 meters long and 17 meters wide, no less than 30 meters tall. It was also equipped with a helideck that added instability. Like the DSM, it weighed 4,000 tons. Once again, the lifting towers were called into action and the strand jacks lifted their loads slowly but surely. The living quarter module was hanging from the towers, but needed to be installed at the correct height so that once floating alongside the UPM, it could be easily and swiftly installed. Fagioli built 10 support towers made of tubular steel and installed them on 12 transport beams. These were mounted astride 5 lines of SPMTs, and the whole unit was more than 40 meters high, with a center of gravity 30 meters high, and a tipping angle of just 8 degrees, an extremely unstable building. Now it had to be moved towards the barge that adjusted ballasting as it took on the weight of the living quarters. The living quarters approached the UPM. By the end of 2017, the massive utilities and processing module was ready to be once again skidded onto a massive barge. At the other end of the bay, the rest of the Hebron oil platform had been completed. Once again, the whole gravity-based structure that would one day rest on the ocean floor was sunk beneath the waves.
Well, any project and concept is unique. They are custom made. First of all, they need to adapt to the water depth where they are placed. There is oil and gas storage needs. We have environmental conditions. We have the reservoir. And there may be also linked to other systems or platforms offshore or onshore.
The top side of the Hebron oil platform was floated over it and attached to the protruding central tower. Once again, the whole oil platform was refloated, ready to be towed out.
Every time when I see a group of people put together, doesn't know each other from before, executing projects like this in an excellent manner, that is a big moment, yes. But of course, towing out of structures when you see the work is completed is of course also a good feeling, yes.
Another sunset over the frigid north, where the demand for black gold, the precious natural resources that fuel our everyday life, buried deep beneath the sea, gives impetus to the most massive engineering.
A new day rises over the Venice lagoon. The water in the lagoon is between just 4 and 14 meters deep. But when the 550,000 square meters of sea surface are whipped up by adverse winds and tides, the sea level can rise by up to 2 meters, flooding the city that was built on millions of wooden stakes that hold the hundreds of sandbanks and islands together. The architectural treasure that is Venice is threatened by the very element that made it prosper in the past: water. Its position and wealth have been its ultimate downfall. With a dwindling population, the city is literally being broken down by tourism and climate change. But saving Venice has become a World Heritage priority, and billions are being spent to stop the rot. Over the last century, the once proud city of Venice has suffered the humiliation of a declining population, the invasion of new barbarians dragging trolley suitcases up and down its streets, huge cruise liners whose wake flattens the lagoon sea floor, and periodic flooding by the waters of the lagoon itself, as overuse of the subterranean aquifer has caused the city to subside. In adverse wind and tide conditions, the Adriatic Sea pushes into the lagoon through the 3 openings of Lido, Malamocco and Chioggia, and raises the sea level just enough to flood the streets and homes of this ancient city.
Quello che è cambiato non è ovviamente il fatto che oggi ci sono le acque.
What has changed is obviously not the fact that today we have flooding and 200 years ago we didn't, but it's the frequency that has changed, mainly due to 2 combined effects. On the one hand, we have the subsidence. The overall level of Venice and its surroundings has dropped by several centimeters, estimated at between 10 and 13 centimeters, together with the phenomenon of sea level rise, the increase in the average sea levels caused by climate change, and as a result, high and medium high waters are more frequent during the course of the year.
Avere acque alte, medio-alte lungo l'arco dell'anno.
La progettazione di per sé ha molti aspetti di.
The design has in itself several important, difficult aspects. The resistance of the structure overall with respect to the loads, and the many systems including rotating the legs, and transport. They were certainly not easy to develop, but they were the most fun.
Certamente facili da sviluppare, però sono stati anche quelli più divertenti.
The so-called acqua alta is a phenomenon that occurs mainly in the winter months, when high tides in the Adriatic Sea coincide with winds that blow towards Venice, creating a flood wave that invades the navigation channels and spreads over the lagoon until it reaches the city itself. Some tourists may find the flooding of St. Mark's Square fun, but the heart of the most romantic city in the world is also the lowest point of Venice, and the flooding causes inestimable damage to the foundations of St. Mark's Cathedral, one of the most ancient in Italy. Once the water rises above the level of the special marble used by the engineers who built the city over the centuries to provide insulation of the brickwork, then the facades of the buildings begin to suffer dramatic erosion. These buildings are designed to be light, as they stand on millions of wooden piles, so any damage to the brickwork can cause structural damage too. The high waters are eroding not just the foundations of the city, but some of the world's most beautiful works of architecture. The lagoon is an ecosystem in danger. Not only the city, but the hundreds of islands and wetlands that make up this unique landscape risk being lost forever, with the added complication of rising sea levels. Bounded in the north by the river Sile and in the south by Brenta, for centuries the Venetians fought a battle to stop the lagoon silting up, even deviating the course of inland rivers. Access to the sea was Venice's source of power, and the lagoon was its natural defense. In the last 30 years, the situation has been reversed. Trade now goes to Marghera, the city that drained the water table, and the sea has become a threat. The walls of Venice are the massive floating barriers that will stop the sea from flooding Venice. Giovanni Zarotti is the lead engineer on the Mose project. He has seen it grow over the years and now heads up the team that will bring it to fruition. The new Venice consortium of Venetian enterprises that has come together to build the Mose, or Modulo Sperimentale Elettromeccanico, the floating walls that will defend Venice from high waters.
Il Mose è un'opera che prende avvio dopo gli eventi del 66.
Mose is a project that began after the events of 1966, with the exceptionally high tide that caused flooding of huge parts of Venice and the massive damage done to the city's cultural and monumental heritage. As a result, there was a significant intervention with the creation of an infrastructure to control the medium-high tides. That means tides that reach 1.10 meters above the average sea level and can go as high as 1.96 meters, as happened in 1966.
Moving the massive engineering parts that make up the Mose fell to one of the world's leading heavy lift companies, Fagioli. In 2012, the company was engaged by the new Venice consortium to lay the floating barriers and concrete housings that cross the Lido entrance to the lagoon. It was the beginning of the final phase of the Mose project. However, the Malamocco and Chioggia entrances required extra engineering, as they are even deeper and wider than the Lido entrance. Fagioli's engineer, Tommaso Favaretto, was the lead engineer on the project.
Sono state costruite rispetto al progetto precedente degli elementi sia orizzontali.
As compared to the previous operation, we added horizontal elements, crosshead beams. We lengthened them to allow us to cover the geometric parameters of the walls of Chioggia and Malamocco.
Caratteristiche geometriche
They weigh more and are larger than the Lido Treporti walls. Here we're talking about 400 to 450 tons of weight to move over several tens of meters.
Su una lunghezza di diverse decine di metri.
The Mose is one of the largest works of civil engineering built in Italy. Over the last 10 years, it has provided hope that the city can be saved from sinking under the waves. The world waits with bated breath to see if the walls of Venice will actually save the city. The project is one of the most complex works of civil engineering ever built in Italy, designed to save the city from the periodic flooding.
Le opere sono ufficialmente state avviate nel 2003.
The project was officially launched in 2003, and a lot of the work, most of which has already been finished, were works of civil engineering. So, for example, the concrete housings that form the base of the work, and the housing for the walls, consolidation work, and the essential infrastructures that the whole project needs that are located at the lagoon entrances.
The Venice lagoon is 80% made up of wetlands that are partially submerged, and only 12% is made up of islands, while the city of Venice is actually held together by millions of wooden piles pushed into the mud and sand. The tides that so threaten the city are also its only real drainage system. Twice a day, clean water enters the canals and dirty water is taken away. As a result, there were several prerequisites for the Mose that the designers undertook to respect, not only to maintain the overall visual aspect of the lagoon, but also to ensure free exchange of water between it and the open sea.
Conseguentemente si è avviata tutta una fase progettuale.
So we began the planning process, but the Italian government set a certain number of prerequisites for the construction process, and there are two main ones: that the construction should have a low visual impact and should not modify greatly the overall aspect of the lagoon. And the second was that it should not substantially change the hydrodynamic exchange between the open sea and the lagoon.
Later, the plan involved restoring the natural ecosystem that contributed in the past to slowing down the flooding process. Access for ships and seawater into the Venice lagoon is through 3 openings in the long sandbank that makes up the barrier with the open sea. The openings are at the Lido of Venice, at the small fishing village of Malamocco, and in the south of the lagoon at Chioggia. The Mose concept is based on a system of floating barriers to close these 3 openings when the adverse wind and sea conditions are forecast. They are massive steel walls that can be filled with compressed air when necessary, rising to the surface, making a floating wall.
Quando si entra nella fase operativa, il meccanismo principale è quello che vede la...
When the system becomes operational, the main process involves air being pressurized, that is, then pumped through pipes into the barriers. When the pumping begins, the barrier that is usually filled with water, because it has openings that ensure it is filled with seawater, is filled with air that pushes the water out of the same openings. And through the simple floating process, the barrier is subject to the Archimedes effect and rotates upwards and emerges above the sea surface.
La paratoia subisce la spinta di Archimede, ruota ed emerge rispetto al pelo libero dell'acqua.
The floating barriers lie flat on top of huge underwater bunkers, with access tunnels that allow for maintenance, where the massive hinges around which the barriers rotate are housed. The mobile walls are built to fit snugly on the sea floor, and once floating one beside the other, create a watertight wall of steel. In 2013, the first mobile walls were installed at the Lido entrance to the lagoon. This entrance was so wide that it was artificially divided into two to allow easier management of the massive structures. In these extraordinary images, dating back to the first campaign to lay the caissons, the concrete housings for the barriers, we see the area where the housings were built being flooded. One by one, the caissons were pumped with air and floated. Fagioli used a special catamaran to position each 12,000-ton concrete housing over the 12-meter deep trench dug into the sea floor, where four 300-ton capacity strand jacks lowered it onto bags that were slowly emptied to provide the soft landing needed for absolute precision. The exact location of each caisson was guaranteed using GPS positioning and radar. It was one of the most complex moves Fagioli had ever carried out.
I cassoni sono stati prefabbricati sostanzialmente.
The housings were prefabricated in an area that was drained of seawater. So they were built on the bottom of the sea, and they are cellular housings, so made of concrete walls, but partially empty inside, so able to float.
Ma parzialmente vuoti all'interno, per cui in grado di galleggiare.
So in this case, at San Nicolò and Chioggia, they were built on land that had been reclaimed from the sea that was flooded, and they were floated.
In qualche maniera sottratta al mare e portati in galleggiamento.
Then the walls themselves were laid. They weighed 210 tons. They were floated out to the location above their concrete housings on a barge, and then lifted by a specially designed gantry crane and lowered into place so that they fit perfectly onto the hinges. In a rare visit to the underwater bunkers, located more than a dozen meters under the surface of the lagoon, the actual configuration of the concrete housings for the mobile barriers can be seen. A tunnel with lifts at each end allows for regular inspection of the hydraulics and electric systems that are at the heart of the Mose. Each hinge is housed in its own room with watertight access doors. A reserve tunnel ensures there is access under all conditions, even when the bunker-like construction is flooded. Malamocco is a pleasant fishing village on the strand that separates the Adriatic Sea from the Venice lagoon, and is also the place where hundreds of ships pass through every year to get to Porto Marghera, the great industrial and petrochemical hub of northern Italy. The channel is particularly deep, and the caissons, or bunkers, were built close by as they were particularly heavy. While at Lido, each of the caissons is able to house 2 barriers, here each concrete underwater bunker houses 3.
At Malamocco, the system we used was different, although the housings were essentially the same. They were built on a bank built above sea level and then moved via a system of rollers and taken to the synchrolift, which is a kind of massive elevator that lowered them into the sea, and then they were floated away and tugged to their final destination, and then they were sunk again.
Con dei rimorchiatori fino alla zona di varo e lì nuovamente affondati.
Building such a huge work of civil engineering was easier said than done. The concrete structures built at Malamocco first had to be lifted and then moved onto the huge synchrolift crane. Then they were lowered into the water to be tugged out to the open sea and dragged to the place where they were to be sunk. The sea floor had to be specially prepared to house them, so that their roofs were flush with the natural depth of the sea in those locations. Then they had to be emptied to allow access to workers to prepare the electrical wiring and compressed air pipes that activate the enormous floating walls.
The size of the housings varies from one lagoon entry to another, but the largest are 60 meters long, 40 meters wide, and 12 meters high, and the whole of the height has been encased level with the seafloor. Weights differ too, but we are in the area of 22,000 tons of concrete. The barriers have a very important element, that is, the hinge that allows them to rotate and also receive all the surface piping that carries air, that make them rotate and float. So there are corridors that allow them to run through the housings.
E quindi c'è la necessità di poterli percorrere questi cassoni.
The depth of the lagoon entrances at Chioggia and Malamocco required significant modifications to the original gantry crane that was used in 2013.
Il canale di Malamocco ha peraltro una...
The Malamocco entrance has an extra difficulty that was dealt with during the planning phase and in the construction phase, that we had to guarantee the continued passage of cargo ships going to Porto Marghera, the industrial area of Venice. In this case, the seafloor is deeper, as I said, 14 meters deep. So, as a result, the barriers are the longest, because as they rotate and float, they have to push a greater volume of water. So they are almost 30 meters long, 29 meters and 3 centimeters.
E quindi arrivano a sfiorare i 30 metri, 29 centimetri per la precisione.
Non esisteva un'attrezzatura adatta all'installazione della paratoia per...
There was no pre-existing tool to install these barriers due to the geometry and the dimensions of the barrier, as well as due to the location they were laid in.
È quello della laguna di Venezia, per cui ci si trova di fatto in mezzo all'acqua.
We were working in the Venice lagoon, so over water, so we needed a gantry crane to lower these barriers onto their housings.
Di carro ponte per calare le paratoie in posizione di installazione.
During the whole time, ships continued to enter and exit the lagoon along the deep channel carved into the lagoon floor to allow tankers and cargo ships to reach Porto Marghera, one of Italy's great industrial cities. It is close to Venice, and the wake of the ships contributes to flattening the lagoon floor, which in turn speeds up the flow of floodwater. To combat this, the New Venice Consortium is rebuilding a system of islands and wetlands that are designed to not only slow the floodwaters, but also to encourage the return of wildlife.
Nell'ambito appunto degli interventi promossi
Among the projects promoted by the state, by the Commission for Public Works and former Inland Waters Office, or Magistrato delle Acque, and taken forward by the consortium, also involve the reconstruction of the wetlands, areas of land that are covered by water during high tides, but emerge at low tide, that are home to unique flora and fauna. Apart from preserving habitats, these areas also make the hydrodynamics inside the lagoon more efficient.
Più efficace l'idrodinamica interna della laguna.
Here at the Fagioli headquarters near Reggio Emilia in northern Italy, engineers are working on the technical specifications of a gantry crane that is soon to be handed over to the New Venice Consortium to allow the regular maintenance of the floating barriers that have become Venice's new walls.
La cavalletta ha un ingombro in pianta di circa 50 metri per 25 metri.
The gantry crane is about 50 meters long and 25 meters wide, and it's about 35 and 36 meters tall.
Le gambe sono costituite da delle torri tralicciate e da dei tubi circolari.
With regards to the legs are made up of a trellis tower, which is built from tubular steel, and it's 26 meters tall, held together by top frame beams, on which the long beams are placed, and these hold the strand jacks and the fishing beam.
Per sorreggono I nostri martinetti e di conseguenza la trave pescatrice.
The Fagioli engineers, however, had other concerns. Their new gantry crane had to be tall enough to reach the deeper caissons of the Malamocco and Chioggia openings, some 14 meters deep, and at the same time be small enough to be safe and stable on the barge.
I fondali di Chioggia e di Malamocco sono più alti.
The openings of Chioggia and Malamocco are deeper, Malamocco, which is the deepest, is 14 meters deep, between the surface and the top of the housings. So we needed to make the crane taller, adding several meters of leg length, so compared with the previous 9 meters, we had to add 6 more meters of trellis tower.
An engineering complication made their lives even more difficult. This gantry crane was built especially to lay the 58 walls that make up the barriers at Malamocco and Chioggia. The massive trellis structure had to be able to lift the larger floating barriers that weighed more than 400 tons and were wider than the Lido barriers. The calculation of the forces applied to the different parts of crane had to be precise, especially because the crane had one potentially weak point.
We built a structure called a mid-head frame, a rotating frame that's located halfway down the legs, which allows the legs to be rotated, gull wing-like, reducing the vertical height of the gantry crane. This allows it to be transported from the assembly yard all the way to the location where the barriers are to be laid.
The special tool that the Fagioli engineers have at their disposal is the strand jack, the hydraulic jack that is able to slowly lift hundreds of tons of weight, using a concept that is simple in itself, but highly complex to build. A strand jack is a hollow hydraulic cylinder with a set of steel cables, the strands passing through the open center, each one passing through 2 clamps, one mounted to either end of the cylinder. The jack operates in the manner of a caterpillar's walk, climbing or descending along the strands by releasing the clamp at one end, expanding the cylinder, clamping there, releasing the trailing end, contracting, and clamping the trailing end before starting over again. The real significance of this device lies in the facility for precision control. When many strand jacks are activated at the same time under the control of a central computer system, the lifting power of each individual steel strand can be multiplied infinitely. Fagioli famously supplied the near 100 strand jacks that rolled the Costa Concordia onto the artificial sea floor so that it could be readied for refloat.
All the strand jacks respond to the same central computer that's controlled by an operator, and the combination of the operator's skill and the capacity of the software allows full control of movement and loads, so as to guarantee that the whole operation sits within the project parameters and the requirements of the object being lifted, that is often very delicate, so needs very fine lifting tolerances, high precision, and above all, need to respect safety limits.
Fagioli designs its own strand jacks, and on this entirely new gantry crane, the sets of strand jacks did different jobs. The folding legs needed 4 strand jacks each to open and close the joints.
La cavalletta di varo, gantry crane, è equipaggiato con 4 martinetti di sollevamento.
The gantry crane is equipped with 4 main strand jacks, able to lift 300 tons, the AL300s. The transport beam is equipped with as many AL300s, and the crane also carries another 8 50-ton capacity strand jacks to enable the rotation of the legs, and these are used to rotate the legs one way to open them, 4 are needed for this, and 4 are needed to close them.
E 4 per la chiusura.
The logistics of getting the gantry crane to Venice were so difficult that the company decided to build it directly close by. All the parts were manufactured and delivered to a construction site at Porto Marghera.
La cavalletta viene...
The gantry crane is assembled and built at a site near the place of operation, but not on it. The place was ex Area Bagnan.
Si chiama Area Pagnan, ex Area Pagnan.
It was built here, first building the individual parts and then putting them all together with the legs closed, so rotated upwards.
Viene assemblato tutto l'assieme con gambe ruotate, quindi con le gambe rivolte verso l'alto.
Getting the gantry crane onto the barge was a especially difficult task. Luckily, Fagioli also owns hundreds of SPMTs, self-propelled motorized transports, that not only are modular, so can be as long or as short as needed, but can also lift their loads. Fagioli uses SPMTs in all their heavy lift operations. SPMTs are modular, wheeled flatbed vehicles that are remotely driven and maneuvered. They are able to move in any direction and even rotate, as each set of wheels is independent. They can be as long or as short as the user wants, as well as hydraulically raising their load. They are seen here moving the whole center section of a ship that has been lengthened by slipping this new segment into the middle. The versatility of the SPMTs is shown by how the wheels swivel 90 degrees to move the load perpendicularly to the original direction of transport.
La cavalletta è circa 800 tonnellate.
The gantry crane weighs 800 tons, so moving 800 tons together with the transport beam was not easy, because the center of gravity is very high.
Il baricentro è molto in alto.
So stability had to be guaranteed at every stage, both during transport and during operations.
To move the gantry crane to lay the Mose barriers, they were slid under it and lifted it. Slowly but surely, they drove onto the barge that was specially ballasted to maintain stability until the weight of the crane was central. It could now be taken to the construction site closer to where the floating barriers were to be laid. A special transport beam was loaded with it, so that once on site, it could be raised and lowered as needed.
Una volta che è assemblata, come tanti pezzi del Lego.
Once the gantry crane was built and put together like so many Lego bricks, it was transported using another system built by Fagioli, called the transport beam. And it was loaded onto the barge using self-propelled transports, and then taken to the worksite, where it was prepared for the installations.
Dove viene preparata per l'installazione.
Now came the delicate moment of actually taking the crane to the location of the massive concrete caisson.
Alla banchina di cantiere viene sbarcata.
Once we reached the worksite, the crane was disembarked and turned 90 degrees into the installation position. Then it was re-embarked in the installation position and then taken to the point above the concrete housing where the first barrier, or the barrier in question, was to be lowered and then set up.
E lì viene posata.
The barge made its way to the pre-established site over the caisson hinge where the floating barrier was to be placed. It was then held in place by cables attached to posts, and the barge's pilot's job was now to keep it stably in the same place, using a joystick that pulled on the cables to counter any current or wind.
La chiatta con a bordo la cavalletta viene ormeggiata mediante degli argani.
The barge with the gantry crane on board was then anchored using cables attached to winches, and the cables were attached to foundation poles located at the lagoon entrances. And the positioning of the barge was managed using a positioning software based on GPS and regulated by pulling on the cables by winches until the gantry crane was in the correct position for the barrier to be laid over the housing.
In posizione nella posizione corretta per essere calata dalla chiatta fin sul cassone.
This time, the legs had to protrude over the side of the barge so that they could be unfolded and lowered into place. Neoprene pads had been attached to the bottom of the legs so as not to damage the concrete surface of the caissons. The stranjacks pulled open the legs, which were then locked to provide maximum stability. The lifting device lowered the gantry crane onto the surface of the caisson.
La cavalletta nei suoi piedi, nel base frame, ha
The gantry crane was equipped with a centering cone located in the base of the frame, which is a male part that's wedged into the receptacle on the surface of the concrete housing. Once in position, the gantry crane is lowered until the male cone, that's on the foot of the crane, enters into the receiving cone located on the housing surface.
Entra nell'alloggiamento del cassone di soglia.
The barge was withdrawn and went to collect the huge yellow floating barrier that had to be placed on the underwater hinge. The fishing beam was lowered by 4 300-ton capacity stranjacks, and once the barrier was safely attached using electrically operated couplings, it was raised, and once again the barge could slip away, leaving only air and water between the barrier and its place of final location.
Quindi la paratoia viene agganciata alla trave pescatrice che è agganciata alla cavalletta di varo mediante gli stranjack.
So the barrier is attached to the fishing beam that's attached to the gantry crane via stranjacks that allow vertical movement. The fishing beam is equipped with hydraulic systems that push against the gantry crane to allow for horizontal movement, so we get millimetric positioning both vertically and horizontally.
Impianta e verticale che ha precisione quasi millimetrica.
Slowly but surely, the fishing beam lowered the floating barrier 14 meters underwater until the male part of the hinge fitted snugly into the female receptacle where it could be fixed. The fishing beam could be withdrawn once again. However, the whole operation involved laying floating barriers in as little time as possible. So as soon as the first was fixed in place, the transportation beam was brought out on the barge, and once again, the gantry crane was lifted out of the water. The stranjacks pulled up the legs, and once again the barge was tugged to the next position. Laying the Mose floating barriers took months, in every kind of weather that the Venice lagoon could throw at the equipment and the men.
In all, there are 78 barriers, but more were actually built because there are 2 spare barriers for every lagoon entry. And the reason for this is that these barriers will have a periodic need for maintenance. So, in order not to leave the place where the barrier has been removed without, while it is being repaired, the extra and identical barrier is positioned there as soon as the barrier due for maintenance is removed.
Diciamo che le condizioni di progetto per le macchine sono
Let's say that the operating conditions for the machines were very severe and were respected. During operations, the humidity, the rain, the cold of winter still exist, and people who work on site get sun when it's sun and rain when it's rain.
Prende il sole quando c'è il sole e esposto alla pioggia quando c'è la pioggia.
Each operation required up to 15 workers to maneuver the massive gantry crane that Fagioli had specially built to do the job. Worker safety was one of the chief priorities of the company. As the seasons came and went, the floating barriers of Chioggia and Malamocco were securely laid, and the great civil engineering project approached completion. The next steps involved testing it.
Le paratoie del sistema Mose sono in realtà
The Mose floating barriers are already operational in experimental mode at Tre Porti to check they work and in order to set activation parameters. Here, all 20 barriers have been laid, and they have been raised several times, and so the entrance closed several times.
di sollevamenti e quindi di chiusure della bocca di porto.
Although billions of euros have been spent on the Mose project, it will only be activated under certain specific conditions. Conditions that threaten the whole of the city, rather than just the area of Rialto and St. Mark's Square, the lowest points, which will continue to be flooded even during relatively low high tides. The buildings of Venice are light, with as much as half of their outer walls open with windows. Rotting brickwork and wood severely undermine the structural integrity of the palaces and churches of this once thriving city.
A metà del 2020
Around 2020, we expect the whole project to be finished, with the support plant working, so fully operational, and with Mose available to protect Venice from high tides. By the end of 2021, we will have finished the ancillary work, more to do with the environment and architecture, that do not influence the operation of the whole project.
architettonica che però non influiscono sulla funzionalità dell'opera.
Although the Mose project is only dedicated to isolating the lagoon from the Adriatic Sea in adverse weather conditions, saving this unique city from oblivion has been costly.
Possiamo dire che il Mose
We can say that the Mose, once it is finished, will have cost in the area of 5 billion euros. This should be compared with Venice's cultural and monumental value, which I think is priceless.
storico-monumentali di Venezia, che credo abbia un valore inestimabile.
The most iconic cathedral square in the world has now also been included in the overall plan to save Venice. This cathedral is unique, with its Byzantine mosaics and amazing crypt. Every high tide floods it and destroys more of this 1,000-year-old brickwork.
Vicino alla Basilica di San Marco,
Close to St. Mark's Cathedral, we have a value of 70 centimeters above sea level. So even with 70-centimeter tides, due to the many tunnels under St. Mark's that were built to drain rainwater from the square, the inverse flow of the tide runs up these tunnels and begins to flood the square. So the committee and the consortium are working on a plan to insert anti-reflux valves against the tide, allowing the draining of rainwater, but stopping reverse flow of high tides.
e il ritorno d'acqua dell'alta marea.
Today, with the Mose nearly completed, one of the many threats to the very survival of Venice has almost been removed. There are many others. But as the sun sets over the most beautiful city in the world, Venetians hope that the tide has turned.